Hi, folks. This time we are talking about transition metals. Now, we've been marching across the periodic table looking at reactivity trends. We started with group 1, the alkali metals, then we talked about group 2, the alkali earth metals. Now we're going to talk about this big bunch, the transition metals in the middle. So this is going to be group 3 through 12, so this whole big bunch in here. And they're less reactive as you go from the left to the right. So there's more reactivity on this side and less reactivity on that side. Why am I doing one talk about this whole bunch? Well, they have a lot of properties in common. First off, most of them are silver and shiny. These are going to be our industrial metals. These are the ones that make our modern age, that build our buildings, our gizmos, our machines. They are commonly mixed together. Some we see in pure form, but very often they are alloyed. And alloy, the word alloy means a mixture of metals. So when they're in a molten form, they are mixed together, and it's wonderful because then you get a mix of properties. Sometimes you want something that is harder or lighter or shinier or more of a conductor or less of an electrical conductor, and you can create some designer metals by mixing them. I want you to also know the word galvanized. If you go to your local hardware store, you might want to get a galvanized bucket or galvanized nails, and that means coated with zinc. Zinc is way over here on this far right-hand side of the transition metals in the less reactive side of this pile. And we coat things with zinc to prevent them from being oxidized or rusted. So here's a metal that we are using to coat other metals to protect them. And that is a wonderful idea because it is way the heck on this far right-hand side. We've got chromium that we use to make things pretty and a whole bunch of other lightweight transition metals to make aircraft. But let's talk about these in bunches. One of the groups in the middle of the transition metals are the ferromagnetics. Ferromagnetic metals are metals that are around iron on the periodic table, and we can use these to make wonderful magnets. All matter has some magnetic properties, but these are the big three. These are the ones that if you want to set out to make a great magnet, these are the goodies. Iron, cobalt, and nickel, they all make fabulous magnets. You can change the amount of magnetism really quickly in them. And so these are our ferromagnetics: iron, cobalt, and nickel. The coinage metals. The coinage metals sit right here. Now our reactivity trends get less reactive as you go to the right, and the coinage metals sit on top of each other: copper, silver, and gold. Now, these guys have a low ability to interact with chemical reactions. That is why we use them to make coins out of. You do not want to make your currency out of something that is going to react with the air or react every time it got wet. And that's why ancient man, thousands of years ago, chose these metals to make their coins out of. So copper, silver, and gold, because of their low rate of reactivity, this is why they are our coinage metals. And frankly, we make an awful lot of jewelry out of them as well. Of course, silver and copper are more reactive. Gold is the least reactive of this bunch, and it is for that reason that it is highly prized for jewelry and for monetary uses. Transition metals tend to make colorful compounds. If you're going to find something in nature, not biological, not a bird or a flower or things like that, but something that is a rock or a mineral, and it is a pretty color, by golly, I would bet you money it's going to contain a transition metal. Transition metals tend to make very colorful compounds, and copper is one of those. Copper makes, depending upon how it bonds, and we'll talk about this multiple ways of bonding in the next week or two, copper can make blue or green compounds. If you burn copper compounds, it will produce a really beautiful medium colored green flame. If you see copper corroded pipes, one, be worried because your piping might be in trouble. but it will have this beautiful kind of a bluish green cast to the color. This is copper sulfate. Copper sulfate has this gorgeous dark blue color to it, and it is used a lot in jewelry and in ornamental work because artists love that the oxide on copper has this gorgeous kind of bluish green color. This photo is of multiple different colors of, copper compounds. Some are very pale, some are very dark, some are so dark blue that they're almost black, but all of them are shades of blue or green, and that has to do with how copper bonds. Iron is another one that bonds in a couple different ways and produces multiple colored compounds. The one we're most familiar with is rusty red. We've all seen rusted old cars, rusted old nails, and things like that, and that is that color. If you know somebody in your life or you've met someone with natural red hair, the red didn't come out of a Miss Clairol bottle. The red hair comes from the fact that there is iron bonded in the melanin, the pigment that goes into their hair, which is pretty nifty. And that's where that red coloring comes from. The hemoglobin in our blood also contains iron, and it's those iron compounds that react with oxygen that gives us nice oxygenated blood that gives us this beautiful rusty red color. We've all had a cut on our hand or something and seen that red blood. But veins, the blood is kind of this aqua blue. Well, iron bonds in two ways. It has two different ways of bonding. And if you have iron bonding with lots of oxygen, it makes this rusty red color. If it bonds in a low oxygen environment, it makes this aqua blue color, which is where the aquamarine gemstone comes from, where the blue comes from in your veins. And this is the beautiful prismatic pool out in, I believe it is, I was going to say Yellowstone, and I might be wrong. One of the national parks, you're going to tell me I'm wrong later. And this grand prismatic pool, and this is different bacteria in a low oxygen environment in the center, more oxygen on the outside, and depending upon oxygen level, the bacteria change color, which is so incredibly nifty. A lot of the paint and pigment that is used by artists is colored with transition metal. You may be familiar with cobalt blue. Cobalt blue comes from good old metallic cobalt. Hundreds and thousands of years ago, artists would mix their own paint, mix their own colors. And so to be an artist, you had to be pretty good at chemistry and finding the right rocks to crush up with the oil to make your own oil paint. Cadmium yellow is a color. If you go to an art store and buy a yellow, you buy cadmium yellow. And that comes from the element cadmium and one of the forms of cadmium, one of the ways it bonds. Red has always been an expensive color in stained glass, in paint, things like that. And because of the fact that gold does not bond very often, but when it does, sometimes it will produce some absolutely stellar, gorgeous red ions. Titanium white is again a paint color when you go to a paint store, and it is a beautiful, beautiful clean white. There's a lot of titanium oxide on the moon, and that is one of the reasons why the moon reflects light so incredibly well. Lead is another compound that comes with two different primary forms. It can bond in different ways when it makes two different oxides, and it tends to make these colorful compounds. Sometimes it makes red lead, and sometimes it makes white lead. Now, not in its pure form. In its pure form, it looks like lead. It's gray and silver. But when it bonds with oxygen, it's going to make a white oxide or a red oxide. And that is why the Wisconsin homes of the past, you'd have a red barn and a white house. That was real common because of the fact that these paints were made using these oxides. You may have heard stories of don't let children chew old paint because they're going to contain lead. Well, nobody put lead in the paint because they were trying to hurt small children. They put lead in the paint because the oxides of lead were such incredibly pretty colors. And it was just many years later that people found out that the paint chips were dangerous to children. And for a weird thing, lead paint chips also have a weird property that they actually taste sweet. And that's the other reason they can be very hazardous to children. They don't know any better, and they actually taste sweet, which is kind of bizarre. Now, this is kind of weird trivia because I live in Wisconsin. The Wisconsin Badgers football team. First off, why are they called the Badgers? I mean, yeah, we have badgers in the state of Wisconsin, but they're called Badgers because of lead mining in the southwestern corner of the state, down north of Galena, Illinois. In this corner of the state, there was a lot of lead that was being mined. Why would we mine that much lead? We'd mine it for paint. And that's why it was a big deal. Why are the colors red and white? Well, those are the two oxides of lead that were used to make red and white paint. A little trivia next time you're watching some football. Now, we've been going across these transition metals, and they are more reactive here and less reactive there. And so as you go across, we're getting to the edge of the metals, and the metals end on that stair-steppy line. So I want to talk a little bit about aluminum, which is cuddled up right there, kind of off the edge of the transition metals, but here is so cool. As you get all the way over to aluminum, we're talking about a metal that is very, very stable. How stable is it? Well, aluminum foil is pure aluminum. That's one of the pure elements that you probably have sitting around in your kitchen. And it is so pure and so stable that we wrap baked potatoes in it, and you can cook in it, and we drink pop and beer out of it, and it can be used to make airplanes. Why do we know it's stable? Well, from experience, but also its position on the periodic table. It's over here on this far right side of the metals. It is a stable element in the metals, and that's because of its position. To give you kind of an idea about these metal reactivity trends, that metals on the left are more reactive and they get less reactive as you go this way. When you're talking about metals, let's talk about just this group: sodium, magnesium, and aluminum, and when they react with oxygen. When they react and make a hydroxide. If you have sodium hydroxide, you have drain cleaner or lye. If this gets on your hand, you're going to get nasty, nasty, nasty burns. If you have magnesium hydroxide, one family over, this is so gentle that you drink it. It's going to make you poop, but you can drink it. And by the time you get way over here, when you have aluminum hydroxide, this is part of deodorant, and you put this on your skin to help prevent you from perspiring and smelling. So it is just depends on where the metal is. It can be something that can be hazardous to your body to something that is beneficial to your body. Position is a big deal. So metal reactivity, it's more reactive as you go down, more reactive as you go left. And those are the most reactive metals is francium, and they're less reactive as you go up and right. Okay, next time we're going to come back and we're going to start talking about the non-metals.